Why don't we get going, guys? And then as people trickle in, they can trickle in and say hi. Welcome everyone. You're in week 3 of our Intro to AI workshop for medical students. Some of you might be new, some of you might be returning people, all of which are most welcome. This week, we're going to be learning a little bit about some key terminology, such as supervised versus unsupervised learning. Some people were asking questions about that last week, and this is the week you're going to get answers to those questions. We're going to hear from our other instructor, Prash, as well as Ricky, who you all should know, about things like logistic regression, decision trees, some of the fun stuff around machine learning, and things that people might not even consider machine learning, but really are. As always, ask your questions in the chat as we go. Zoe and myself will be moderating, and we will try our best to keep you engaged. So without further ado, I'm going to be quiet and welcome Ricky.
Sure. All right, thanks, Rohit. All right, so this week we're going to talk about machine learning, which is an exciting topic. It's all modern data science, and it's what we came here for. So I'm just going to recap some important key concepts from the last 2 weeks. One is the definition of machine learning. So AI, we know, is just the ability for some system, machine, program to sense its environment and accomplish some sort of complex task. Now, machine learning is a technique within AI, specifically so that every time our program or machine completes the task, it'll look at its error and update itself and keep improving itself. The analogy that machine learning is like a robot that shoots a basketball and then looks at how it missed and then tries to adjust and shoot more accurately. Last week, we also talked about how dangerous some sort of data interpretations can be. So for instance, these distributions all have the exact same first order statistics and Pearson correlation coefficients, but they're all obviously different distributions. So relying on odds ratios and coefficients to make conclusions sometimes has its limitations because it relies on these linear relationships. As we know in biology, not everything is linear. We can't just add variables up. So sometimes we have to look at more complex relationships. That's where machine learning comes in. Machine learning is really good at modeling complex interdependencies between variables. We also talked about the prerequisites for your data set for machine learning. One is that we want a large varied data set. Right? So this is from one trial that was guideline changing. When they published this trial, they changed the guidelines, and these guidelines are used at emergency departments everywhere now. They had about 42,000 samples for their machine learning algorithm. Now, I know there's a rule of thumb that's 10 times the number of samples. That's not a hard rule of thumb. Sometimes you can get away with less. Of course, the more the better, and the more data you have, your machine learning algorithm will be able to adapt to new scenarios. And this isn't just limited to machine learning. Any sort of data analysis and predictor that you want to make, you want to throw as much data in it as possible to really test its performance. So get lots and lots of data, right? Don't get just 30 or 40 samples. That's probably not enough for generalizability. We talked about overfitting, which is a big problem in not just machine learning, but any sort of data science. Sometimes when people build their models on their entire data set, they can get really high accuracies if they just fit the model on that data set. So on the figure on the right, this is really, really high accuracy, really, really high R squared, whatever metric you want. But it's remarkably overfitted so that when you add new data that comes in, the model won't be able to capture it. Whereas the model in the middle is what we want. And the way we avoid this is with a technique called cross-validation. So one of many ways we avoid it. One is to get as varied a diverse data set as possible. And then with your data set, you want to split it up. You want to split a subset as your training subset. Generally, it's 80-20 split or 70-30 split. But then you only take that 80% for training your model. The last 20%, you put it aside until you test your model. And that'll really test your model on new data because it hasn't seen this data before. It hasn't tried to force a fit on this data. And then you can repeat this 5 times. If it's 10K-fold cross-validation, you repeat it 10 times. And then you average the accuracies. And that'll give you a really good snapshot of how your model is doing. So always, 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 always cross-validate your model. never, ever, ever build your model on the entire data set, and never, ever, ever, ever train on your testing data set. I recently reviewed some papers that did this, and they had 0.8, 0.9 area under the curve, but then when an auditing paper reviewed it, their accuracies were 0.5 to 0.6. So it's ingenuine if you report your accuracies by modeling on the entire data set. But don't get me wrong, you can if your goal is not inferential statistics, if you just want to be descriptive and you want to calculate like the mean, the variance, maybe even the odds ratios, and just report that, then you can use your entire data set. Right? You can say that from our data set, these are the odds that we observe. But you cannot say we built a predictor by modeling on the entire data set. So now, before we move on to Prash's section, are there any burning questions about the topics we covered in the previous week? I have about a minute and a half. I can answer any confusions or questions we have before moving on. So feel free to type in the chat or speak up. I'll give everyone a minute before we move on. What's the best medical journal for AI? Great. So, great question. So, I think the cream of the crop right now, specifically for image analysis, is a conference called CVPR, Computer Vision and Pattern Recognition. This is where all the top cutting edge technology gets published, and it's also great. It's a great place for you to look. They have a lot of medical related AI applications there too. That's a top technical paper in a technical conference. In terms of for more medical analysis, there's a conference called Nikai, and that's where the top sort of medically oriented, it's not just AI, but it's any sort of computer aided analysis. That's where they publish. So these are the two conferences to keep an eye out for. They always come up with some exciting stuff every year. Okay. So if you have any other questions, you can feel free to type it in the chat as we go along, and then Zoe, Rohit, or I can answer them. But otherwise, I'm going to hand it over to Prash, who will talk more in detail about machine learning specifically. And I'll stop sharing my screen.
Awesome. Thanks, Ricky. All right. I hope everyone can see this. So in case you guys missed the introductions in the first week, my name is Prash. I'm a PhD student in biomedical engineering at UBC. And I'll be taking over the rest of today's session, and really we'll be diving deep into some core fundamental concepts in machine learning, which are really important to know if you want to build your knowledge and keep learning more about machine learning and eventually using it. So for today's agenda, we'll do a very quick recap of when to use AI, what it is, and just note here that I'm going to be using machine learning interchangeably with artificial intelligence, or AI, even though Ricky explained the difference between the two earlier. These days, whenever someone talks about machine learning or AI, they mean the same thing when it comes to at least medical related applications. Then I'll explain the two main different types of machine learning algorithms. This is supervised and unsupervised learning. And then I'll talk about two main supervised learning techniques, which may seem very basic, but are very important to know because many complex models build on these methods. We'll also talk about decision trees, which are very relevant to clinical practice. And then I'll talk about the machine learning training process in detail as well. So to remind you of this delicious memory from the first week, remember these are my truffle slides, which I've designated as being important and something worth remembering. So machine learning, or AI, is a computer program or an algorithm that is able to identify and detect patterns, and it uses those patterns to create a model so that you can predict outputs on new data. And so always have that definition in the back of your mind. Now, being more specific, you have generally speaking, two major types of machine learning algorithms. And these are called supervised and unsupervised techniques. So supervised learning is when you have labels for the outcome that you want to predict in your data. And unsupervised learning is simply the opposite. You don't actually have labeled data when it comes to any type of outcome. Now, you might be wondering how this even works, like how does unsupervised learning work if you don't have any labels? I will explain that with a very simple example. But here's another sort of made up case. Let's imagine you working in an ICU, and for each patient or it doesn't have to be an ICU, but any clinical ward, and for each patient, you collect their blood pressure and their resting heart rate. And then the thing you're interested in is if they have diabetes or not. So you tabulate these results, you collect, I don't know, like 100 patients, and you want to be able to predict if they have diabetes. So if you want to be able to predict that, then you need to have labeled data on whether they have diabetes or not. And then, you can label this based on your blood glucose level measurements or their previous history. But let's say you didn't actually have that outcome variable. You don't know if they have diabetes or not, then if you can still feed this data into a learning algorithm, but that would be unsupervised learning because you aren't able to really predict if someone has diabetes or not because you don't have labels. Now, remember, Ricky defined these different columns last time. The blood pressure and the heart rate columns are known as your features or your independent variables more classically. And then the outcome, the thing you're interested in predicting, is known simply as the outcome or the dependent variable. So in a very, very basic example, let's say you plotted, in the supervised learning case, you plotted the blood pressure on the x-axis and the resting heart rate on the y-axis. And then in this particular situation, I'm representing the blue circles as the patients without diabetes and the red triangles are patients with diabetes. Now, you could have a classification supervised learning algorithm which is able to define this boundary between the two groups of patients, saying that, okay, this is the optimal boundary between these two groups of patients. So now that when you have a new patient in the ward and you collect their blood pressure and resting heart rate, let's say this new patient is this green square, you know because this patient lies on the left side of this line that they likely don't have diabetes. And so that's an example of supervised learning. Now, on the other hand, unsupervised learning is mostly, since you can't actually predict whether they have diabetes or not, you can use it to do something called clustering or dimensionality reduction. So in clustering, you can still plot the data like you did before, but in this case, you don't actually know if there are any differences between these groups. So even though I've plotted the different shapes and colors here, you don't actually know that these groups are different. But there are unsupervised learning algorithms out there that would be able to identify that these patients, and these patients actually lie in separate groups just based on, for example, the distance between the points. And so you could just collect data from the ward without any labels, but just some characteristic features like blood pressure and heart rate, and then find groups within that data. And it could turn out maybe later on when you examine the patients further that these groups actually have some clinical significance. So for example, it could be diabetes, or maybe it's something else, the risk of going to ICU or something like that. The second main type of unsupervised learning algorithm is something called dimensionality reduction. And this is reducing the number of features you have in your data, and so reducing the complexity of your data. So let's say in this case, you plot your blood pressure and heart rate as before, but you notice that your data has a relationship between the features, which I've plotted in this sideways parabola here. So here you can see that the blood pressure and heart rate are actually related. And there's very little variance across this line, but a ton of variance as you follow this line. So you can actually use that information to combine or to simplify your data a bit. So instead of having separate features for blood pressure and heart rate, you can define a combined feature, which I've just made up as heart rate squared minus blood pressure. And you just use that instead because you can see that this explains the variance in your patient population the most. And so by reducing your data complexity, you can then go on to do more machine learning if you want with supervised learning algorithms, or you can do other analysis. So this is another way that unsupervised learning is used. Now, there's actually a middle ground, and this is, it has many terms, but one of the most common terms is called semi-supervised learning. And this is when you have a few labeled examples from maybe like, let's just say you have 10 or 20 patients that you know have diabetes, but there are actually hundreds and thousands of patients that you're interested in analyzing. So in this case, you can first use the labeled patients to find a classification boundary. And then you can add the unlabeled data. So the unlabeled data here is shown in the black circles to modify your classification boundary. And this is sort of just helpful. The first few label points help you get started, and then you can analyze the rest of the data. So we can actually plot all of this in kind of a spectrum showing the different classes of algorithms. And as you go this way on the red axis, you need less and less data. So obviously unsupervised learning is on the very extreme here, and then supervised all the way on the left. But the trade-off is, as you have less labeled data, which means the cost of annotating that data is less, the predictive power goes down as well. So if you really want to be able to predict if someone has diabetes or not, or any other kind of prediction, then you really need to have more labels. And the more complex that model, or the more complex that prediction, the more data you need. And in this case, I know I've sort of plotted these scatter plots, but this is equivalent to imaging data as well. So let's say you have some X-ray scans where radiologists have carefully marked out where lung nodules are visible. So that would be an example of labeled data, which you can put into a supervised learning algorithm. But on the other hand, let's say you just had like 100 X-rays, no one has labeled them. You can still feed that to an unsupervised learning algorithm, and that would be able to find different clusters, differences within the data itself. Okay, so most of the time when we are talking about medical machine learning, we're almost always talking about supervised algorithms. So I'm not really going to focus on the rest of the semi-supervised and unsupervised algorithms for the rest of this course. We're mainly going to be looking at supervised machine learning. Okay, so I hope that was not too complicated, but if you have any questions, let me know or speak up. Otherwise, I will move on in 10 seconds. So does unsupervised learning reduce the function on its own? Yes, some algorithms will reduce the function on its own, like it will output how the features relate to each other exactly. So yeah, they will. And you can also see how much error is explained when the learning algorithm does that for you. Okay, moving on. Okay, so there are, once again, two major types of supervised learning algorithms. And you might be already familiar with these, but they're very important to know in your head so that when you're coming up with a new problem or you're starting a new machine learning project, you can kind of think of which one of these classes your problem falls into. So the first one is regression, and the second type is classification. So if you remember from the first week when I was talking about, once again, that made-up case where you have patients with different weights, and you're plotting how many days it took for them to stop smoking. And I fitted this linear relationship, or this linear trend between the two, between the input variable and the dependent variable. This is an example of regression. And on the other hand, when I was talking about diabetes, a patient either has diabetes or they don't have diabetes in this case. And so that's an example of classification. And to be more specific, for regression, the output variable that you're trying to predict has to be continuous, which means there are infinitely number of values that you can have for that particular variable. So for example, you could be measuring someone's blood glucose level, and that's on a continuous scale, or you could be just diagnosing them with having diabetes, and that's a categorical variable. So if it's categorical, then you have a classification task. So someone either has diabetes or they don't, there's no in between. And remembering from last week's lecture when Ricky was saying that even for categorical variables, everything has to be coded numerically. So even though the labels of interest are sort of no diabetes and diabetes, when you input that into a machine learning algorithm, you would just input them as integers. So no diabetes could be represented as a 0, and then diabetes is as a 1. But there is no 0.5 or anything like that. Okay, so linear regression is pretty straightforward, but I'm going to specifically be talking about the function that is being modeled when we do this. So when it comes to linear regression, everything that's happening is really just explained by this equation, which is the equation of a straight line. And I hope that's familiar from hopefully like high school math or whatever. Typically you learn this as y equals mx plus b. In the UK, we learned it as y equals mx plus c. I have no idea why. But hopefully you remember that m explains the gradient or the slope of the line, and then b is the y-intercept of the line, or the bias. So this equation that I've written here is exactly the same, except just a couple of the letters have changed, or actually just one of the letters has changed. The w is now representing the m. And this is such a simple equation, but it's very important to understand what each of these symbols really means. So here, y is the dependent or the output variable. So in this case, this is the number of days it takes a patient to stop smoking. X is the input or independent variable, or the feature. And this is the weight of the patient. W and B are both known as parameters of the model. And an alternative name is weights. And that's what the W stands for. And this is what the linear regression algorithm is trying to learn, because you already have these and these from your input data, but you don't know the slope and the y-intercept. And so a machine learning algorithm will somehow try to find these values out. And so when it does that, you have an optimum value for W and an optimum value for B. Then when you get a new patient, you can estimate the number of days it would take for them to stop smoking. Now, this seems super simple, but it's very important to just know that this is how linear regression works, because many complicated models, including neural networks, just build upon this very simple equation. Now, logistic regression is an extension of linear regression, but very confusingly, it's actually used for classification. And this is confusing because remember I mentioned that there's regression and there's classification. But in this case, this term logistic regression is used for classification problems. Though the reason the name is regression is because it's an extension of the linear regression problem, and because it's modeling a continuous function. And so it's just important to remember that. When I show an example, it'll become clear why that is. So don't be too confused. So logistic regression equals classification equals you have categorical output variables. So in this case, in this example, let's say you have a bunch of patients and you've done some tumor resection and biopsies, and you're able to map out the different tumor sizes and whether the tumor ended up being benign or malignant. So in this kind of thing, you can either just have a benign tumor or a malignant tumor. So that's a categorical output. And then you can essentially, what logistic regression is trying to do is fit an S-curve, also known as a sigmoid, to this data so that you can find the optimal threshold for tumor size so that you can categorize future tumors into being possibly malignant or benign. So in this case, we fitted this S-curve to this data. We could pick a threshold at where the 0.5 line crosses here, which is approximately 7.5 centimeters. And then you could draw a line here and then classify any data below this as being benign and any tumors above this being malignant. So the equation for this line is almost the same as the linear regression example. But in this case, you have a 1 over 1 plus the exponential function. And then importantly, this function within the parameters is exactly the same as your linear regression equation. So this works in exactly the same way, but now instead of getting a straight line, you get this sigmoid curve. All of these things mean exactly the same. So why do we use why do we use logistic regression as linear regression instead of linear regression? I hope this is fairly obvious, but if you imagine doing linear regression for this kind of data, is not very helpful because if you get, say, a new tumor, the Y value being predicted is down here, which doesn't really make a lot of sense. And it's not bounded at the categorical values that you want. Whereas for logistic regression, this sigmoid curve is bounded on the y-axis to being between the two categorical values that you have. And so as I mentioned, once you fit a logistic regression function, once you fit the sigmoid, you can then define a threshold to best explain the data that you're seeing. And then you can decide that based on that threshold, data above that threshold and data below that threshold belong to the two separate classes. And so logistic regression is great when you have just one or two classes. Here I'm just showing a one-dimensional example, but of course this is equivalently applicable to multiple dimensions. But as your data gets more and more complex, logistic regression becomes less and less valuable. So here's just an aside on how these parameters are learned. Like I mentioned, W and B are the things that we're trying to find out when we have these algorithms. But how does that actually, like, how does the algorithm come up with numbers for these? So this is all through optimization. And this is, in my opinion, a very interesting branch of mathematics and machine learning. There are many different optimization techniques that these algorithms can use to come up with these. You don't actually need to know any of this. You'll very rarely need to play around with these very much. But just so you know, these are the terms, they exist. And essentially what they do is that based on a cost function that either you define or you let the algorithm choose, the machine learning algorithm iterates over many steps to try and find the optimum parameters for W and B until it reaches a minimum value for that cost function. And once it does, it settles on that value for W. And here is a very slow playthrough of the learning in progress for linear regression. So here you can see that there's this blue scatter plot and the green line is being fit to the data very slowly. With each iteration, a new scatter point is being evaluated and the parameters for W and B are being slowly updated here until the error is minimized. Now, unfortunately, this animation doesn't actually finish, but you can see that slowly the green line is turning clockwise to eventually fit the data here. And obviously, modern systems can just do this in microseconds, so you never actually see this happening. It's just fitted instantaneously. This is the same thing for logistic regression, but much quicker. So we can see that once again, we have these points belonging to class 0 and class 1, and these weights are updated with every iteration. So you can see W and B here, and you can see that over time, the S curve is fit so that the cross entropy loss in this case is at a minimum. I hope these animations work well over Zoom, but if they don't, feel free to watch them again when we share the slides. Another thing that I didn't mention, which is interesting, is that sometimes people interpret these values on the y-axis as probabilities because they're usually bounded by 0 and 1. That's not strictly true, but you can think of it as the probability of the output belonging to class 1 or class 0. That's one interpretation of it. It doesn't really matter as long as you know that these are meant to be categorical values. Okay, so any questions? Yeah, that is a fun fact. Optimization is a very interesting topic. If you ever have time, just like watch some videos on it on YouTube. You will see that it comes up everywhere in math and engineering. I'll just wait 10 more seconds for any questions. Since we don't have that many or fewer people this time around, I'm also happy to just answer questions over Zoom, so you can just speak up if you have any questions. All right, moving on. So I kind of alluded to the fact that logistic regression is not always the most suitable for complex data. So when does this happen? Let's say we had the same example with tumor size and malignant and benign tumors, but your data is a bit more difficult to separate. Now your malignant tumors are actually, some of them are smaller as well. And now let's say we drew the threshold at the 0.5 mark. We can see that we actually misclassify some of our data. So some of these malignant tumors are inaccurately being classified as being benign. And then this particular tumor here is inaccurately being classified as malignant. So this means that if we draw in one dimensional, if you draw a decision boundary, which is just a straight vertical line, and you can't really separate your training data, it means your data isn't linearly separable. And if your data isn't linearly separable, then logistic regression won't really be able to capture the decision boundary very well, and it won't be able to classify the samples very well. And you can sort of visually just visualize this. So if you imagine you had more samples down here, more big benign tumors, and you had more small malignant tumors, then the S-curve won't really be able to fit those points. And this is what that looks like in 1D, but this is what it looks like in 2D. So going back to this 2D plots of heart rate and blood pressure, these two groups and the top here are linearly separable because you can draw a straight line in 2 dimensions through both of the groups, and you can separate them completely. So in these two examples, logistic regression would be suitable to use. But in the bottom here, you can see that you cannot draw a straight line between the two groups to separate them. In this case, on the bottom left, there's this red triangle, which is not possible to separate. And in this case, you have nonlinear data here because the decision boundary is nonlinear. And so for both of these, logistic regression wouldn't work. And so as you can see, before you even pick a machine learning algorithm, it's very important to be able to visualize and understand the data that you have so that you can pick the most appropriate algorithm. Okay, so this is where decision trees come in. Decision trees are another classification technique, but they can also be used for regression. But the good thing about decision trees is that they can come up with nonlinear decision boundaries. They're very flexible because input and output variables can be both continuous or categorical. And decision trees are completely interpretable, which is why they are useful for situations like medicine, where you want to be able to justify why you categorized a particular patient as having diabetes or not. So it's used a lot in medicine. Like I said, this example is taken straight from the American Academy of Family Physicians, or is it association? Anyway, so in this example, a patient comes in with dizziness, and then you can go through this flowchart or decision tree to figure out what to do with them. So based on a set of features of the patient, based on the symptoms and any other tests that you do, you can figure out if this is a psych issue or if it's more of a neuro issue. And so having these decision trees to classify your data is extremely interpretable, and you can actually classify data very well with this. So we'll go through an example. I'll just see if there are any questions. Okay, so Shelby asked, how does this account for outlier data? I wasn't sure what you're talking about. Was that for decision trees or was it for decision, oh, for regression? Logistic regression, yeah, so obviously you can have some outlier data even if your data is linearly separable. So for example, here in this bottom left example, we can see that this data is mostly linearly separable with the exception of this particular red triangle here. And so when you visualize your data and look at it, you can say, well, that's just noise, and maybe that data was mislabeled or it was just misrecorded. So we will ignore that, and that's totally fine. In fact, it's better not to accommodate every single outlier you see, because that is an example of overfitting. So imagine if you came up with a decision boundary and used a nonlinear classifier, and you just wrapped a decision boundary around this triangle and background. That would be an example of overfitting, because it's likely, given that it's only one sample here, that this is just noise or erroneous. On the other hand, when you have something like this, you can clearly see that there is more of a pattern to these red triangles and it's not just based on noise. So it's very important to evaluate whether or not you're going to overfit or underfit your data. And we'll talk a bit more about that later today when I look at when I talk about what kind of errors you can measure when you're looking at if your training, validation, and testing is going well. But good question. Okay, so here I was talking about decision trees. So here's an example. I'm sticking with the Lord of the Rings theme here. I hope you guys know and like it, so you'll understand it. But anyway, Treebeard is a character from Lord of the Rings. He's extremely old. So let's say that because he's thousands of years old, he's witnessed and remembers many battles throughout history. And he's deciding when they should attack Isengard. So he knows all of this data from his previous experiences and whether or not the attack was successful in the end. So that's this last column, and this is the output variable that you want to predict. And so Treebeard remembers the weather on that particular day, the temperature, humidity, and the wind, and whether the attack was successful or not. So he wants to know if the next day they should attack or they should keep waiting. So you have all of these features, which in this case are all categorical. So you can see that there are no continuous numerical values here. It's just yes, no, or like different categories. So you can create a decision tree, which is very simple. You can start with the weather and then decide what to do based on the different conditions, and so on and so forth until you have come to a final decision. And then you can measure, based on this, you can actually measure the error of your classification on your training data and to know if you've done a good job or not. This is equivalently applicable if you have numerical continuous values. So let's say for humidity, besides just high and low, you actually have a measurement for percent humidity, and same for wind, you actually have a continuous measurement for wind speed. You can make a decision tree based on numerical values. So instead of having categorical explanations, you have thresholds based on the value, cutoff values for humidity and wind. And so you can come up with a decision tree like this. So how do you come up with that decision tree? This is the simple algorithm that is used in machine learning. So first, the best attribute is selected. I'll explain how that's done, but in this case, it was weather, and that's your root node. So these are the different labels of a decision tree. So the very top node is called a root, and that's because you can imagine this as an upside down tree. The very bottom of a tree is the root, and then the opposite, the very end, the decision points are leaf nodes. So you first select the best attribute, and then for each value within that attribute or feature, so we had, remember, sunny, cloudy, or rain, you create descendants of that node. And then you sort the training examples to the appropriate descendant node leaf until your data is perfectly classified, or until you are happy with the classification accuracy. So once you reach this point, you once again select the best attribute and then repeat this process until you arrive at the decisions. So how do you select what exactly the decisions should be? So if you remember, in this case, we decided that the very top, the root node, should be about weather, and then we should look at humidity and wind. Why was that? It's because from that example, it turns out that the weather gave us the most information gain about the samples in our training set. So by using weather, we were able to separate positive and negative data, so whether to attack or whether not to attack, most appropriately. And this is called information gain, but there's many different different measurements that you can use. Probably the most common one is known as the Gini score or the Gini impurity index. So you want to be able to have highest information gain or lowest impurity in your top node when you separate your data. And then as you eliminate the different features, you sort of just pick the next highest feature or the next highest information gained feature until your decision tree is complete. And so, for example, on this side, the low information gain feature is not very helpful because if you separate data based on this, you don't actually end up with different categories in either of these nodes. So one issue with decision trees is that it's very easy to overfit them based on how big your tree is. So for example, in this very simple case, let's say you have a great feature that can perfectly separate your two different categories, like from your blue circles from your gray circles, then that's great. You don't need to actually go further. But let's say you don't have that kind of feature available in your data set. So you separate it first into pretty good categories. You can see that this one is pretty good, but this is not so much. Then you keep separating them until you have perfectly categorized data. But you can see that in this case, most of these categories or most of these decisions only have one sample in each of them. And so you might question how generalizable this is, because if you get new data, how confident are you that it's going to end up perfectly categorized based on these decisions? So it's very well characterized and understood that as the size of your tree, and in particular the depth of your tree, gets larger, the generalizability decreases. So you can see that the accuracy on your training data, that's the solid line, will obviously keep increasing as you increase the depth and the number of nodes in your tree. But on new data, on test data, the accuracy decreases. So you really want to be somewhere here where your test accuracy and your training accuracy are closest together, and both are high. And so this is a correctly fit tree size, and this is overfitted. All right, so neural networks are another, obviously, AI model that we can use to both do regression and classification. It's suitable for very complex relationships, but unfortunately, the opposite of decision trees, they're not very interpretable. And we'll talk about this a lot next week. So don't worry about it for now, but I just wanted to include this so that you know that neural networks do fall into the same realm of sort of supervised learning. And funnily enough, here is a decision tree for the other algorithms that you can use. Here are just a bunch of terms that I'm going to throw out in case you're interested. You can always look them up. So we didn't talk about these in this series, but you know these are also equivalently applicable. You have k-nearest neighbors, support vector machines, and random forests, which is an extension of decision trees. And based on how much data you have and how complex your model is, you can pick these different classifiers, or sorry, these different models to do your classification or regression. And this flowchart sort of guides you through how to pick a model. Just for fun, this is scikit-learn, which is a Python machine learning library. And we will use this in our programming exercise or programming workshop in a couple of weeks. So you'll be able to actually play around with these different functions and do all of this for yourself. All right, so I'm going to look at the chat again, see what we have. Yeah, so if you have any questions, once again, just type them out or speak up. Otherwise, I'll move on. So what does classification for medical imaging look like? That's a good question. And there isn't a simple answer to that, because you can either classify an image as a whole, or you can classify each pixel in an image. And so if you classify an image as a whole, then that's kind of treating that whole image as just one class. So you can just say, for example, this X-ray has lung cancer, this X-ray doesn't have lung cancer, and you can separate your patients that way. But on the other hand, if you want to know where the lung cancer is or where the tumor is, then you have to have labels for each pixel in that image. And of course, that's a more costly process, because a medical expert will have to first give you some labeled images for X-rays telling you where the lung tumors are. And so when you have pixel-wise classification in medical images, that's more classically known as medical segmentation, because you're segmenting particular parts of the image to belong to one class or another. There are also levels in between. So instead of classifying a whole image to classifying just pixels, you also have things like detection. So instead of classifying pixels individually, you can just classify a region belonging to a particular category or not. And once again, that lies on a spectrum as well. If you guys are interested, we can definitely talk more about this next week, or I can take some time at the end of this session to talk about it. So clustering, k-means clustering is one algorithm to do clustering, but that's not the only method that you can do it. It's one of the most popular ones. So k-means clustering actually is very similar to the k-nearest neighbors classification method, but there are different ways of doing clustering. So yeah, clustering is just the problem, kind of like you want to do clustering. That's the problem you have at hand. And then k-means clustering is one of the tools to solve that problem. And at the top of my head, I can't think of the other algorithms out there, but yeah, I guess you have Gaussian mixture models and other types of clustering algorithms that can be used as well. And k-means is just one of them. All right. So moving on. Oops. What does the training process look like? So let's say you've picked an algorithm out based on whatever you know, and you want to do supervised learning. What do you do next? So you have to make sure you visualize the data to know what it looks like. And in fact, I'm going to say that you should have done that before you visualize the data, and then you've picked the algorithm. So always remember, this is important just in case you don't pick an incorrect algorithm or something that won't actually be able to model your complex data very well. So exploring the data, visualizing it is one of the best ways to explore the data, but also actually manually looking at the values of your data. Do you have any missing values? Do the measurements make sense? Did you get noise in there somehow? Are you missing some values that you didn't realize? Just actually looking at the data, whether it's images or a table, is very important just so you get a feeling for it. So after you've done that and you've picked your algorithm, you need to prepare your data so you can then put it into your algorithm. And once again, Ricky talked about this last week, but preparing your data involves cleaning it. So removing any outliers that you don't believe represent your data very well, or you believe are noisy, filling in or removing any missing values that you may have. You also need to decide which features you want to use. So here, what you could potentially use some unsupervised learning to do dimensionality reduction or clustering to figure out which features are important. And just because you have all the features of a patient, like just because you know their age, just because you know their sex, doesn't mean you need to use them to be able to predict something accurately. Obviously know which variables are going to be continuous or categorical so you can format them properly, and then know what your output variables are. You can have just one, or you can be predicting multiple different things. So it's just important to know that both for the, well, it's important to know that in your head so that when you run the algorithm, you're inputting the correct things and not making a mistake, because it's very easy to just sort of do this very quickly and then realize much later on that you've made an error and that your accuracies are not believable. Okay, so this is once again one of those truffle slides. It's very important to know how to split your data and feed it into your algorithm. So Ricky mentioned, doing cross-validation and having your test and training sets. But really, more specifically, you need to have a training set, a validation set, and a test set. And these are all different things. And you need to know that the test set is your very final way to check how your model is doing. And it should only be used once to evaluate your model performance. And to sort of explain why this is and what these different sets mean, I'll use the analogy of taking an exam. As medical students, you have to take a ton of exams, unfortunately, and so you have to study very hard for them. But it could take many months to study for an exam. So you need to prepare, you need to learn concepts, and that's the equivalent of sort of training your algorithm. Your algorithm is trying to learn the different parameters of the data. It's the same as you trying to learn, the anatomy of the heart, how to read an ECG. So we spend weeks preparing for an exam. But how do you know that you're actually making progress? Well, you might decide to sit some sort of practice test that you have from a textbook or you bought online. And this would be the equivalent of validating your AI model. So you let it train, and then you actually validate it on a practice test to see if it's learned anything and if it's doing well. And you might do this yourself because you want to see yourself perform well in the practice test before you take the exam, so you feel confident. And on the other hand, if you're not confident and you fail miserably in your practice test, then you can maybe push the date of your final exam further. And then the test set is your final exam. So you've trained, you've validated, and you're happy with your performance. You're happy with the AI model's performance, and you need to take that final exam. So you do that test. And this will tell you at the end how well you did. And it will be able to say, for example, how accurate you were and how accurate your AI model is. But importantly here, you don't actually know the answer key of that test, right? You only get a final error back. You don't know what the true answers were, most of the time anyway. And if you weren't happy with that test, let's say you failed, you might have the option to retake it, but you'll never take the same questions again, right? They'll give you a different set of questions so that there's no potential for you to memorize some of the questions and just practice those. So this is exactly the same for machine learning. You need to have a training set, which is separate from your validation set, which is separate from your test set, so that you know that you're evaluating the performance of your technique fairly and that you're not overfitting to data in either of the sets. So once again, I'm going to go back to shapes and colors. Let's say you have these patients. Each patient is represented by one of these dots, squares, or triangles. Let's say that your green circles here are healthy patients, and each patient has some features that you've collected that are of interest. For example, like their age, heart rate, blood pressure, and so on. Let's say the blue patients have diabetes, and the red triangles have heart failure. And in this particular case, a patient can't have heart failure and diabetes at the same time, so you don't have any mixed data. So let's just imagine these are totally separate, mutually exclusive conditions. Let's say you want to train a supervised learning algorithm, let's say a decision tree, to classify these patients so that when you get a new patient with all the features that you've recorded, you can predict if they have either of these conditions. So then you want to separate your data into these different sets. So this is one possible split. So you have your training data, your validation data, and your testing data. And you'll notice here that I've sampled them kind of based on how much data there was to start with from each of these classes. So there's more of the green data because that's how many we had more healthy patients to begin with. And then there's fewer red triangles because we had fewer patients with heart problems. And so each data is sort of naturally weighted in a way because it's either more frequent or less frequent in the data sets. And there are ways of getting around that, but we won't talk about it, but it's something to notice and to keep in mind. And so most typically, as Ricky said, you have some sort of split, and you can say that's like 80-20. So you could say that that's 80% of all of your data is in your training set, and then 20% is in your validation set. But you got to know that it's actually not like a two-way split, it's a three-way split. So in reality, you'd actually hold off another percentage, it could be 10%, as a testing set that you never show your algorithm or run through your algorithm until the very end. So it would be maybe more something like 10, 20, and 70. And it's very important to have these three different sets. It's a very common mistake, or I would just say something that researchers ignore, having a separate testing set. Most people will only ever report their research on the validation set and often ignoring a testing set. And that's why many times an AI algorithm is actually not generalizable because it hasn't been tested thoroughly enough. And so it has really good validation accuracy, but when it meets new data, which could be seen as test data, it actually performs very poorly. And once again, you can use cross-validation to create different validation splits. So you can shuffle the data around so that you have a different training set and a different validation set. And then you have multiple measures of validation. But you can only do this between training and validation. You can't shuffle your test set with either of these because that will essentially cause data contamination. And it's in a way, it's a way of sort of cheating and making your AI model sound better than it is. And if you're not careful, you may not even know that you're doing this, but it's very important to know that. And once again, this is what Ricky was talking about earlier today and last week. You can split your data into, let's say you do a 5-fold cross-validation, then you can create 5 different shuffles of the training and validation sets. Now, another thing that's very important to know about these different sets is that when you're creating these different splits, you're assuming that the data is independent and identically distributed across the sets. And this is known as the IID assumption. And it comes up everywhere in statistics, but this is very important to know, like, what this means and whether or not you're violating this assumption. So independent, this means that you can't have the same patient appear twice across the set. So you can't have one patient both in the training and validation set at the same time. Or for example, you can't have any other relationship between the samples. So for example, one of the green circles shouldn't be a patient record from 6 months before, and then the same patient came back 6 months later. So you have a second record of that patient, and then you have that again in your sets. You shouldn't have that. So there should be no relationship between samples across sets. So that means samples must be separate and independent. And identically distributed means that patients in each category must be from the same distribution across all the sets. So when you're splitting all of these data sets up, you're assuming that the red triangles in the validation set come from the same underlying distribution as the red triangles from the training set and the red triangles from the test set. Because if they don't, for example, in this case, let's say your test set is actually, let's say you collect data from one hospital in Toronto here. You've got the more vibrant colors. And then let's say your test set is actually patients from a rural hospital in Nunavut or something. And here I've just shown that by having more faded colors. The patients from the rural hospital won't actually be have the same underlying features and not be from the same underlying distribution as the patients in downtown Toronto. For example, they might just have a different BMI and different heights or whatever. And so the results in your test set won't actually, probably won't do as well as you expect because you're testing on a different underlying distribution. Now, most of the time, it's not actually possible to control whether or not your data is identically distributed. You just have data. You just hope that you have split it as fairly as fairly as possibly without violating this assumption. But it's very difficult to know whether or not the underlying distribution is identical. And once again, the best way to get over this is just to collect as much data as possible from as many varied sources as possible. So if you're trying to make an AI model, you want to have thousands of patients across the country, or even better, across the whole world, to represent a varied population so that your final AI model will generalize well. Okay, so once you've split your data appropriately, you can train your algorithm with using the training set. Once it's trained, say you've done 100 iterations, then you can validate how well your model does on the validation set once. You can use cross-validation, as I mentioned. If you're not happy with the performance on the validation set, let's say it does worse than you think, or it totally fails, you can retrain the machine learning algorithm by changing hyperparameters of the model and repeat steps 4 and 5 until you get a validation accuracy that you're happy with or that you think represents the data well. And then at the end, you can then check the results once on your test set to verify that the machine learning model that you've learned has good performance. So I mentioned hyperparameters and parameters, and I just want to clarify what that means, because once again, you will see these terms come up a lot. So I already explained parameters are the same thing as the weights and biases. Those are the W's and B's in those equations that I showed. And that's what is happening during training. The machine learning model is fitting the perfect number for the weight and the perfect number for the bias to the data. But hyperparameters dictate how that machine learning model actually learns. So these are actually other things to do with the algorithm itself. For example, for a decision tree, that could be the maximum depth of a decision tree. It could be the number of iterations you run for, the different optimization technique you use, and so on. And so to go back to that exam analogy, let's say you're studying for a cardio exam. The parameters that you're trying to learn in your brain are actually the knowledge and the concepts of cardio stuff. So for example, how to read an ECG is something you're trying to learn by studying really hard. So that's the equivalent of a parameter. And let's say the anatomy of the heart, that's another example. But hyperparameters are how you learn. So let's say you could choose just to read an entire cardio textbook and learn it that way. Or you could be someone who likes using flashcards a lot, or you watch YouTube videos and take notes. So these are the equivalent of your hyperparameters, the way you learn. And so, for example, you could read a textbook to learn cardio, take a practice test, and realize that you have learned nothing. Then you have to change your strategy. Maybe you say, okay, actually, I need to use some flashcards, or I need to watch some YouTube videos to really understand this. And then you take another practice test again. And hopefully you see that, okay, I've learned something more now. And eventually you do this enough times that you're actually ready to take the final exam. Okay, so how do you measure performance? This totally depends on what kind of task you're trying to solve. So for classification, we hear the term accuracy a lot, and this actually has a very specific meaning in classification. So most people think, okay, like a 90% accuracy or 98% accuracy is really good. So like that is good, but what does that actually mean? I hope from like biostats or like other previous stats exposure, you've probably seen this table a lot. Maybe it was a long time ago and you don't remember, but you can categorize your outcomes from an AI model into 4 different things. So you can have your true positives, which is if the predicted data matched what the actual data was, and same for true negative, if your predict negative values match your actual negative values. So for example, this could be your algorithm says a patient has diabetes and they really do, and your algorithm says a patient doesn't have diabetes and they actually don't. And then same for false positive, when you when your algorithm inaccurately or misclassifies a sample as having diabetes when they don't, or in the case they actually miss the patient has diabetes when they do. So these are all different terms that have very specific meanings. And from this, you can calculate the accuracy, which would be the ratio of the true data over all the data. And then same thing for recall and precision, which is also known as sensitivity and positive predictive value. I'm not going to define them with equations or anything like that, because this is something you can very simply look up when you need to. And remembering this at the time, right now, is not really important. But just know that depending on whether you're doing classification or whether you're doing regression or whatever, you need to use different metrics. And wherever possible, try and report as many as you can, just so people can, and you yourself, understand the performance of your algorithm from a fair viewpoint. And in medicine, this is particularly important because, for example, it's better to know your false negative rate sometimes in case you want to make sure that your machine learning algorithm can catch a very rare disease. So for example, you don't want to miss, I don't know, someone who has a very rare cancer. You want to make sure that you actually catch it. So sometimes it's better to have more false positives at the risk of catching more rare diseases. And so that kind of trade-off is represented on a receiver operating characteristic curve or an ROC curve, which I've shown here. This plots your false positive rate on the x-axis and your true positive rate on the y-axis. And so an algorithm that would just guess and classify patients by chance is always plotted in this diagonal line here. So that's kind of just like using a coin toss to estimate what the patient has. And let's say you use the logistic classifier to train some sort of model. You can plot the trade-off of your true positive rate compared to your false positive rate as you vary different thresholds. And so you can use this analysis to see how good your algorithm is. Specifically, you can measure the area under this orange curve, which is known as the area under the receiver operating curve, to see how good the performance is. And better algorithms or better models will have a higher area. So that means this curve will be more and more towards this 0, 1 point here. Once again, this is all something that you can easily sort of pick up from a biostats textbook or on YouTube videos. So I'm not going to go into very much detail here. So for regression, instead of measuring classification accuracy or recall or anything like that, the most common way of measuring your performance for regression is actually measuring the distance error between the points in your data set and the regression line that you fit. So this is most typically the mean distance error, and that's the vertical distance in this 2D, or sorry, in this 1D example, the vertical distance from each sample point to the line. You can go a step further, and instead of just measuring the performance of your machine learning classifier, you can actually look at sort of clinical outcomes. So how well did my machine learning algorithm help sort of patient recovery? Did it help reduce surgical errors or help reduce ICU incidents, whatever it is that your overall goal is. But you got to know that as you become, as you sort of go into the more applied territory, you're going towards clinical outcomes, it becomes harder and harder to prove that the reason that you have a difference in your clinical outcome is a result of your machine learning model. And so to be able to show these kinds of differences, you typically need to do a randomized control trial or something like that to control everything else that's going on and make sure that it was, you know, the model that you developed that actually made the difference. And then when it comes to things like imaging, you also have specific metrics or coefficients to look at how well you did on segmentation or pixel-wise classification. And so depending on whether you're looking at you know, scatter data classification, image segmentation, image classification, there are metrics out there which are suited to evaluate performance for that. So once again, you should think about your task, think about what you're trying to fit, and then pick these metrics to fairly evaluate your model. Okay, just I think a couple more slides before I'll stop and talk about questions. So I know it's getting a bit late, so I'll just go over this quickly because it's actually something I've already mentioned before. So how do you pick the best model? So obviously you can pick the model with the highest accuracy or whatever metric you're measuring, but you have to also think about whether a 1% or 0.1% increase in that metric is actually meaningful. So always try and apply statistical analysis to those metrics to know if you're seeing a real difference or if it's just sort of statistical noise or chance. And then you might also look at complexity, explainability. How important are these in your clinical decision making and in your application? So that will also help you pick the most appropriate model. And also, it's very important to think about your metrics. So sometimes you want to make sure that you're not looking at just accuracy, you're not looking at just precision, but you kind of want to evaluate both of them together so that you have the best metrics for your particular task. And then I already mentioned this too, as your model complexity increases, usually your prediction accuracy also increases, but the requirement for more labeled data increases too. So your data collection becomes more costly, and there's also more potential for overfitting and instability. So here's a sort of, it's not definitive or anything, but it's a good mental map to think about where these different machine learning models lie on a sort of scale of accuracy and interpretability. So we talked about decision trees today, linear regression, and then neural networks will be next week. Okay, so unfortunately we don't have time to do this live, but I really recommend that you take a look at this website. It actually lets you train a classifier using a decision tree or binary, or logistic regression without having to code anything. You just like point and click, and you'll be able to see the result instantaneously. It gives you a very good understanding of underfitting, overfitting, linearly separable data. So it's very fun to just play around for like 10, 15 minutes to really cement some of the concepts from today's lecture. And then if you're very keen, you can get a head start for exploring some neural networks next week through this website, but we'll talk about more of this next week, so don't worry about it too much. All right, so congratulations
Awesome.
for making it this far. If there are any questions, go ahead. Otherwise, yeah, thanks for being here.
Awesome. Thank you, Prash. And thank you, everyone, for sticking around. If there are any questions, we'll give. Ooh, yeah. Go for it, Prash.
Okay, so bootstrapping is, it's kind of a sampling technique. Was it here? Okay, no. So bootstrapping is a sampling technique where you sort of are able to create new, let's say you pick decision trees as your classifier. So you have a training set and a validation set, but you can come up with new iterations of training and validation sets by resampling from your overall data without replacement. And then you can sort of get multiple different models in the end based on the different data sets that you come up with. And then at the end, you can actually combine all of your models into one final decision. And that's usually called an ensemble. So you can use bootstrapping with ensemble to come up with a more robust model to be able to classify and generalize better. And so that's just a way of sampling your data. It just means sampling without replacement. Oh, sorry, no, actually it means sampling with replacement. It's not the same as cross-validation because cross-validation, you sample without replacement. So you have your training set and your validation set. And that's like that particular split is unique and you can't have that repeated. Whereas in bootstrapping, you could sample 2 points again within the training set if that's what the algorithm comes up with. The reason for doing that is it's like a mathematical reason. It's because then each point has the same probability of ending up in your sets. Whereas if you do validation on cross-validation without replacement, then as you pick each data point to be in either your training or validation set, the probability of the remaining data points being in the subsequent sets increases with each set. So that's one reason bootstrapping is used. But this is a very high level detail. You definitely don't need to know this. I have a ton of Lord of the Rings memes. That's probably my favorite movie. So I'm always happy to include that in my presentation.
All right. I think we'll end it there, guys. Thanks so much, everyone. And we will resume next week with more discussion on neural networks, the latest and greatest in artificial intelligence. Thanks. We'll see you guys next week.
Thanks.
Thanks, everyone. See you next week.